In today's video, we're going to be covering polynomial and rational inequalities. So we're just going to start with a first example here, and that is we're going to solve the following polynomial inequality. And so this is example 1. And part A is going to be x squared minus 4x plus 3 is less than 0. So actually, the first thing I want to do is solve this using a picture, and then I'm going to explain how we can do this problem without having to draw the picture every time. But I want to show the picture first so that we see what we actually mean by this question. And that'll help us interpret the problem in a different way to do the problem a little quicker without drawing the picture every time. So first thing I'm going to do is draw out the picture of this graph. And one thing that we can do as a reminder is we're taking this function here, x squared minus 4x plus 3, and want to graph that down. Well, how can we do that? First thing we can do is we can factor x squared minus 4x plus 3, and that should be x minus 1 times x minus 3. And once we have that, we know that the x-intercepts here for this function are 1 and 3. So we can plot those. We also know that we can find the vertex here by finding negative b over 2a, comma f of negative b over 2a. We know that from a previous section. So what is negative b over 2a? Well, that is positive 4 over 2 times 1, or in other words, 2. So at x equals 2, we'll find our vertex. And if we plug in 2 into the equation, so 2 squared minus 4 times 2 plus 3, this is 4 minus 8 plus 3 is negative 1. This tells us what the y value is. So x or h is 2, and y or the k value is negative 1. So 2, negative 1, our vertex goes here. Our graph of the function, our parabola, should look like this then. And so now let's think about this question related to the graph. The question was x squared minus 4x plus 3 is less than 0. So if we look at the graph, where's our function less than 0? Right? Here's our x-axis, here's our y-axis. The function being less than 0 means we are below the x-axis. So where does that occur? This occurs from 1 to 3, not including the endpoints because we want less than. So our solution should be 1 to 3. Now the question is, how can we do that without having to draw the graph every time? So the first thing we want to do is to factor as we did before. So we're going to factor, and we get x minus 1 times x minus 3. And then what we're going to do is we're going to create a number line, and we're going to put our zeros, which are 1 and 3, we're going to put all of our zeros on this number line. And now let's think about the picture up here again. If we have a function and it hits a 0 on the x-axis, what's going to happen is either in between each of these zeros, either the function is going to be above the x-axis or below the x-axis for every value in between each of these zeros. So what we can do then is, in between each of these zeros, we can determine whether the function is positive or negative, and it's going to stay that way for the entire interval that is in between each of these zeros. So for example, if I supposed that x was 0, so I chose a value, I'm just choosing a random value between negative infinity and positive 1. Here I'm choosing 0. If I just plug in 0 into the function, how do I do that? Well, 0 minus 1 is a negative value. 0 minus 3 is a negative value. So I get a negative times a negative. So what is that? That tells us our function is positive on that region. If we go back and we look at the picture, we see that that's true. From negative infinity to positive 1, our function is above the x-axis, i.e. it is positive. Let's continue on. Pick a value between 1 and 3. Oh, we should probably pick x equals 2. We don't have to. We could pick x equals 1.7 if we wanted to. But x equals 2 should probably be the best choice. So what do? We plug in 2 into our function. I suggest plugging it into the factored form of the function because notice what happens. 2 minus 1 is positive. 2 minus 3 is negative. A positive times a negative is negative. So we can see that everything on that interval from 1 to 3 is a negative value. And that is exemplified by this picture up here as well. Everything between 1 and 3 is below the x-axis. Finally, we want to fill in this last interval here. So let's pick something bigger than 3. How about x equals 5? All right, if we plug 5 in, 5 minus 1 is positive, 5 minus 3 is positive as well. We get a positive times a positive, which tells us that value is positive. So the function value is positive everywhere on that interval. So our original question is, when is this function less than 0? So we have determined that from negative infinity to 1, our function is bigger than 0. From 1 to 3, it is less than 0. And from 3 to infinity, it is bigger than 0. So our solution is from 1 to 3. It's the interval from 1 to 3, which is exactly what we got before. This method, though, is what we're going to be doing every time for the remainder of these problems. So let's move on and do part B of this same problem. So we're going to do part B, and this is going to be x cubed plus 2x squared minus 4x is equal or greater than 8. So again, we want to solve a polynomial inequality, but the polynomial is different this time. First thing we want to do is solve for 0 here on the right side, so we want to set it equal to 0. So we're going to get x cubed plus 2x squared minus 4x minus 8 is equal or greater than 0. And now the problem looks like the previous problem, except we have a cubic instead of a quadratic. So what do? We want to factor again, just like we did in the last problem. Factoring is going to be a little bit more difficult in this case. So as a reminder to factor of how to factor, we first recall that it is the factors of what zeros do we have here, right? To be able to factor, we know from the last section we can find the zeros of the polynomial. Well, how do we do that here? Zeros of this polynomial, excuse me, are factors of the constant term. Divide by factors of the leading coefficient. And we can find that this is plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. All of these together are the possible solutions to this polynomial up here. They're the possible zeros, rational zeros of this polynomial. Right, the factors of the leading coefficient were just 1 and negative 1. So if we divide all of these by 1 and negative 1, we just get these values again. So I kind of skipped that part here. But anyways, these are the possible rational factors of, or possible rational zeros of this polynomial. So if we plug in 1 and negative 1, we're not going to get a 0. let's go ahead and plug in 2. If we plug in 2 into this function, we will see that we do in fact get a 0. So right, this is 8 plus 8 minus 8 minus another 8, which is 0. So we see that 2 is a 0. So x minus 2 is a factor. So what does this mean? This means we can use the information from the previous section to determine the rest of this polynomial when we factor out or divide out an x minus 2. So we divide by x minus 2 here. All right, x goes into x cubed, x squared times. X squared times x is x cubed, and we have a minus 2x squared here. Subtract this off, and we get a positive 4x squared. Drop the 4x. X goes into 4x squared, positive 4x times. Finish out the division as such. X goes into 4x, positive 4 times. 4 times x minus 2 is 4x minus 8. And we see that this will be 0, so we get a remainder 0, which is good. We want that. So what we can see here is that x cubed plus 2x squared minus 4x minus 8 is equal to x minus 2 times x squared plus 4x plus 4. We can further keep factoring this. This should be x plus 2 squared. So what that tells us is that there are only 2 zeros. There is negative 2 and positive 2, right? We get negative 2 from here, and we get positive 2 from here. So we only have 2 zeros here. And we go on and we finish this problem out just like the previous problem. We want to pick a value in each of these intervals and determine whether the function is positive or negative. So let's pick negative 5 here. Why not? So x is equal to negative 5. Well, if we plug in negative 5 into this function up here, this expression, negative 5 minus 2 is negative. And then we have a negative 5 plus 2 is negative again, but then we square it. So this will be positive, and this will be negative. Negative times a positive is a negative. So when we plug in negative 5, we get a negative value there. And as before, that means the entire interval is negative. It is below the x value, or the x-axis. All right, so let's go on to the next interval. Let's choose x equals 0 here. All right, this is negative, this is positive, so we get a negative times a positive is a negative again. And then finally, let's choose something like x equals 5. Positive on this region, or positive here, positive times a positive is a positive. So a reminder back at the original question. The original question was, when is this function equal or greater than 0? Well, if we go back down to this number line, when is it equal to 0? It's equal at negative 2 and positive 2. And it's greater than 0 when it's between 2 and infinity, when x is between 2 and infinity, so on this interval. So our solution is the value negative 2 union the interval from 2 to infinity, including 2. So this is our solution. And we are done. And so that's how you do all of these polynomial inequalities. We're going to do 2 examples on rational inequalities, and they're going to be very similar. So we're going to solve the following rational inequalities. All right, so part A here is going to be x plus 3 over x minus 2 all over x plus 1 is equal or less than 0. We want to solve this rational inequality. Well, how do we do that? We do this in the exact same way. We have a rational function here. But now instead of just the zeros of the function, we also want to find any discontinuities or holes in the function as well and use those as our breakpoints. So what are the zeros here? The zeros are x equals negative 3 and positive 2. But we also have an issue where x equals negative 1 gives us a 0 in the denominator. If there's a 0 in the denominator, the function doesn't have a value there, but it could also be a point where the function changes from being positive to negative. So we also have to worry about that. So we have the value negative 1 as well on our number line now. And again, all of the values here are just when the numerator is 0 or when the denominator is 0. Those are the points where our function can change from being positive to negative. And those are the only points at which that could happen. So we're going to continue as we did in the previous problems here. So let's pick a value on this interval from negative infinity to negative 3. Let's say x is negative 5 again. All right, and then we plug that into this function up here. So negative 5 plus 3 is a negative. Negative 5 minus 2 is a negative. Negative 5 plus 1 is a negative again. So then we have a negative times a negative divided by a negative. That is a total of 3 negatives, which is an odd number of negatives. If we're multiplying or dividing an odd number of negatives, the whole thing is a negative. All right, let's go on to the next interval. X is negative 2. If I pick x as negative 2, plug that in. Negative 2 plus 3 is a positive. Negative 2 minus 2 is a negative. Negative 2 plus 1 is a negative. So we get a positive, negative, and a negative. That's 2 negatives. So we have an even number of negatives. If we multiply or divide an even number of negatives, the final thing is positive. Let's pick x equals 0 for the next interval. Positive, negative, positive. That is an odd number of negatives, so the whole thing is negative. Let's pick x equals positive 5 for the last one. Positive, positive, positive. Everything is positive, so our interval is positive. Now we want to know, when is this equal or less than 0? Well, we are equal or less than 0 from negative infinity to negative 3. And then we have the interval from negative 1 to 2 as well is less than 0. But notice we should include the 2 because if we plug in 2, we get 0 over 3, which is 0. But if we pick the negative 1, we get something over 0. Well, that value is not in the expression here. So negative 1, when we plug that in here, is certainly not equal to 0 because it doesn't exist. That value wouldn't exist. So we do not include negative 1, but we do include 2 here. And that is the 2 intervals that satisfy this rational inequality up here. We're going to do one more problem, and that'll be it for this section. And that looks like this. So the first thing we want to do is rewrite the problem to make it look like the previous problem. How do we do that? We move everything to the same side. So I just subtracted 2 over x minus 1 on both sides, and we get this. Then we want to make it look like the previous problem. Well, to do that, we need to have a single rational expression. How do we do that? We add the rational expressions here. So on this side, I want to multiply by x minus 1 over x minus 1. And on this one, I want to multiply by x plus 1 over x plus 1. If we do that, we get x minus 1 over x minus 1 times x plus 1 and then minus 2 times x plus 1 over x plus 1 times x minus 1. And let's simplify this. We get x minus 1 minus 2x minus 2 all over x plus 1 times x minus 1. This is equal to, all right, x minus 2x is a negative x, and negative 1 minus 2 is a negative 3, all over x plus 1 times x minus 1. Well, that is equal to negative of x plus 3. I just factored out a negative in the numerator, all over x plus 1 times x minus 1. Now take a moment to think about what are the possible zeros here. Well, negative 3 is a 0 in the numerator, and then negative 1 and positive 1 are zeros in the denominator. So those are the values we want to work with here. So we have negative 3, negative 1, and positive 1. And we do the same thing, right? Because now this expression up here, this right here, is the same as negative x plus 3 all over x plus 1 times x minus 1 is greater than 0. So this is really what we're solving. That is equivalent to this question up here. So we solve that just as we did before. Let's plug in x equals negative 5. If we have a negative 5 here, negative 5 plus 3 is a negative again. This is a negative, this is a negative. But we also have a negative out here in front. So that was 4 total negatives when we plug in negative 5. 4 total negatives multiplied and divided together. We have an even number of negatives, so that is a positive. Let's pick x equals negative 2 here. Negative 2 plus 3 is positive. Negative 2 plus 1 is negative. This is negative as well. So we have 3 total negatives. That means our final solution is negative. Plug in x equals 0 on this interval, right? Because 0 is between negative 1 and positive 1. So we get a positive, positive, negative, and this negative as well. That gives us a total of 2 negatives. Even number of negatives makes the interval positive. X equals, let's pick 2 or 5. I'm going to pick 5 again. All right, positive, positive, positive. This is a negative, so the whole thing is negative. All right, so we wanted to know, when is this thing greater than 0? Well, if we look at our number line here, it is greater than 0 from negative infinity to negative 3. We're not including negative 3 because we want greater than 0, so we're not allowing equals to here. So we do not include negative 3. And union, the other interval, is negative 1 to positive 1. And so that is our solution. Every value of x in between negative infinity and negative 3, or between negative 1 and 1, every value of x there will satisfy this original inequality. Okay, and that is it for this section on polynomial and rational inequalities.